Hi everyone, my name is Yiren. Welcome to our presentation, The Flaw of Averages, Revisiting Graphical Perception to Model Individual Differences in Visualization Performance. Data visualization researchers investigate the effectiveness of different encoding channels by empirical studies. Here is the canonical ranking of 4 chart types. A bar chart is widely regarded as one of the most effective data visualizations. This is due to the inherent perceptual ability of people. So, how can we measure and model the performance of different charts? One well-known study to measure it is the graphical perception experiment developed by Cleveland and McGill. It shows a chart as a stimuli, with 2 elements highlighted. And the question is, what percentage does the smaller value represent of the larger value? The range of answer is from 0 to 100. Then, we actually care about 2 values from each trial. The estimated percentage is the answer given by participants, and the true percentage is the ground truth. From these 2 values, we can calculate the absolute error. Then, Cleveland and McGill used this log error model to measure the performance of the charts. Lower value indicates lower error, which means better performance. However, this log error model is an average observer. It averages the answers from each participant. This failed to capture the individual differences. Thus, this ranking will not reflect all people in population. There is a need for a new model to interpret this data from a different perspective. In this study, we will use a multi-level Bayesian modeling to model data and provide a new angle to the performance of this. First is the experiment design. We select the bar chart, bubble chart, pie chart, and a stacked bar chart as our investigation target. For each chart types, we have a dataset with 20 different data pairs, and each chart type and data combination we repeat them 15 times. So in total, each participant will take 1,200 trials in this experiment. We added training stages before the main study and post-study survey after main study. We have 200 participants take the experiment, 118 able to complete all and 1,200 trials, and 109 of them passed the attention check. Now, with response from 109 valid participants, we will start our modeling. First, by replicating the analysis with log error model. Our results are aligned with previous replications and the original experiment. Next, we will use Bayesian modeling to model the population level performance. For using Bayesian modeling, we will need to choose a likelihood. At this stage, we will just use normal distribution. This is the parameters from our experiment for visualization types, 109 participants, index, and the trials. This model assumes mean absolute error follows the normal distribution. Here is the submodel for mean of error. Beta Visualizat is the average mean absolute error for the visualization type associated with observation I in dataset. There are a few problems in this model. First, this is a population level model. The model cannot capture individual level differences. Second, the normal likelihood did not reflect key constraints of our data, because we know that absolute error on a percentage response scale must be between 0 to 100. In this step, we will use beta distribution replace the normal distribution in our model. The nature of beta distribution is that it is defined on 0 to 1, so it is commonly used to model data with boundaries. The problem when we're using the beta distribution is that it is not allowed 0. But if a participant gives a perfect answer, the error will be 0. So we use the zero inflated beta distribution. This is a modified beta distribution that supports zeros. The mu is the mean parameter, the phi is a precision parameter, and the pi is a zero probability parameter. Now, the likelihood is the proper one to fit our response data. To use a zero inflated beta distribution, we must ensure the mean is within range 0 to 1. At this step, we use the logit link function to map in the domain of mean. The logit is a commonly used link function. It could be used to transfer data domain from 0 to 1 to infinity, or vice versa. This is how the model looks after applying link function and zero inflated beta distribution. Now, can we fit the model to the participant level error instead of mean of error directly? Remember, we have 1200 trials and each unique visualization and the data combination repeated 15 times. Simply fit model to participant level error, we are inflating the number of trials and will cause model overfit. To solve this problem, we introduced the random effect U. This describes how the participants in this observation I deviates from the average for the same visualization type. To apply random effects to the model, we must estimate the correlation between the random effects for different visualizations. This is a model after applies the random effects. These are our model parameters, and this is the likelihood and the mean sum model. We can also have submodels for precision parameter phi and the zero probability parameter pi. This will complete our model. The previous log error model can only show us mean and confidence interval of chart performance in population level, which is very limited angle. By using our new Bayesian model, first, we can examine chart performance in population level in multiple new angles, such as the distribution of error and pairwise comparison. And through our new model, we can examine errors in individual level as well, giving us a lot of interesting findings. Now let's check the results. How our model helps give a more comprehensive perspective to chart performance. First, let's see the population level modeling for each different chart types. We use CDF. Compared to mean and the confidence interval, CDF provides a complete summary of the probability distribution. As we can see, the responses show a staircase shape in CDF. This caused by participants tend to round their answers to certain numbers, such as 10, 20, 25. Next, we did a pairwise comparison between all different charts. This fig shows a comparison between bubble chart and the bar chart. The bubble chart performance is notably worse than the bar chart performance constantly. This is a pairwise comparison for bubble chart and the stacked bar chart. The performance is quite close. The stacked bar chart only slightly better than the bubble chart. Now, let's check the data from individual level. This plot shows the performance of different people in our study. The black line is the average and the confidence interval for each visualization types. Each gray line is an individual observation. The pink line is an example participant we highlighted that do not follow canonical ranking at all, and we can see how poorly this participant is for stacked bar chart. And each cross of the gray line is a ranking change. We can see lots of cross, especially for bubble chart and stacked bar chart. Now, let's make a comparison between individual level chart performance and population level chart performance. The left chart shows the differences in mean absolute error between chart types, and the right one shows the estimated error for each chart type between people. This is a very interesting result. Suppose we want to change chart type from bar to pi, we can expect this much change in error. But if we just switch into another person, we can also expect this much change in error. And you can see if we switch in between other chart types, just like pi to bubble, the expected change in error is relatively small. So the differences between people are larger than the differences between visualizations. With all these insights, let's re-examine the classic rankings. Only 20 to 25% of people follow this ranking according to our estimation. The ranking varies a lot between different individuals. This mean error ranking chart provides a new perspective to consider the performance ranking of these charts. Bar chart may rank number 1 in majority of times, but pi, stack bar, and bubble chart ranking change a lot. We discovered many other interesting findings for the new model, such as performance correlation between charts and the distribution of rankings. Please check our paper to find more details. In this study, we replicated the Cleveland and the McGill graphical perception experiment. We apply Bayesian modeling to the dataset. Then, our model provides many new findings of chart performance. there's a substantial variance between people, there's opportunity for us to provide more comprehensive suggestions for graphical designers. Okay, that's all for this presentation. Welcome to check our supplementary materials through this QR code. Thank you.